conservation momentum just says that the momentum before of all the objects has to equal the momentum after. So the total momentum before a collision must equal the total amount after. So if I have a total momentum of 100 kilograms meters per second before a collision, then I need to have a total after of 100 kilogram meters per second. But there's another way to think of it too, and that's that the total change, well, let's not say total. Let's just say the change in momentum of object 1 must be equal and opposite to, that's not 2, to the change in object 2. Both of those are correct definitions, just like inertia in motion and momentum is mass times velocity. Those are both correct explanations. These are both correct explanations, okay? Whichever one works best for you. The equation is P1 initial plus P2 initial plus any others that there are equals P1 final plus P2 final plus any others that there are. All right, any questions on equation or definition? Okay. So, number 5. Nope, number 9. Good job counting. Why must objects conserve momentum? Now, I'm going to give you the answer in a second in words. I'm going to show you the answer in math. If you like math and this is helpful, go ahead and do it with me. If you don't like math and you think it's going to confuse you, just follow along with what I'm doing. So, why must objects conserve momentum? So here's my equation, right? So initial, we got all that. So if I want to get all the 1's together and all the 2's together, I would subtract 1 final to get P1 initial minus P1 final. I would subtract the 2 over, which would give me P2 final minus P2 initial. Okay, I know final minus initial is called delta, so that's change in momentum for object 2. So I'm going to call this delta P2. And this would be final minus initial if it was negative. So I'm going to pull a negative out and make this final. So if I pull a negative, this becomes positive 1 final. If I pull a negative out of this, it becomes minus P1 initial. This means change, so bring the whole thing over here. We get negative delta P1 equals delta P2. The change in momentum of object 1 must be equal and opposite to the change in object 2. The change in momentum of object 1 is equal and opposite to the change in object 2. That is, right there, Newton's third law. Why do objects have to conserve momentum? That's why. Newton's third law. This right here, that is literally the definition I just gave you, the second definition. That is literally the definition Newton wrote in his book, which I'm sure you've all read. His book from 250 years ago. Ooh, it's 270 now. He wrote it in like 1750 or something like that. Okay? Newton's third law. You don't have to be able to do these steps. It's helpful to know that you get to Newton's third law by using conservation momentum. Okay? And when Newton wrote his book, this is how he wrote Newton's third law. He wrote it as negative P1, negative delta P1 equals delta P2. Any questions? All right, let's do one more example. Oh, yeah. One more example, and then I'll tell you what the homework is. Say again. Here it is, Newton's third law. That is the answer in words, Newton's third law. Yep. Why do objects conserve momentum? It's because of Newton's third law.